to the last last talk of the session, but still interesting. So please, Christopher, your floor is yours.
Thank you. Good afternoon, everyone. Thanks for being here. My name is Chris, and today I'm going to tell you about enabling bounded verification of doubly unbounded distributed agreement-based systems via bounded regions. This is work I've done in conjunction with Nouraldin and my advisor, Roopsha Samanta. Now, you all know distributed systems are infrastructure, whether it's around the house or around the world. They form a critical part of many of the facilities we use every day. Network systems are absolutely everywhere, and their correct operation is important. As such, distributed systems are attractive targets for formal verification. In particular, I want to talk to you today about automated safety verification. Safety properties require our system to never fall into certain bad states. So the system has an erroneous behavior if it can reach any such bad state. Now, ideally, we would like to have our specification and a system definition, throw them into a computer, and have it tell us, yes, this is correct, no bad states can be reached by this system. Or, no, it's not correct, because some bad state can be reached. And under some circumstances, say when the system has a finite number of processes and each of those processes is finite state, we can do that. It's very nice. Unfortunately, however, most distributed systems that we want to verify don't fall into those circumstances. As it turns out, the distributed systems we're interested in are pretty complex. For a start, we want to target systems which are built on agreement protocols like leader election and consensus. These agreement protocols have complex behaviors which are challenging to verify on their own, let alone as part of a larger system. Now, to make matters worse, these systems are often designed to scale, so we don't necessarily know how many processes the system is going to have. Say we consider a system made up of some constant number of processes, let's call that constant number C, and let M be the parameterized model composed of C identical processes all coordinating together. Now, as long as each of those processes is itself finite state, the whole system is finite state, so safety verification is decidable. We can just explore the whole state space and check if any of those reachable states are bad. However, if the number of composed processes is some arbitrary value n, this becomes what is known as the parameterized verification problem. And unfortunately, in its most general form, that's undecidable. Now, as you might imagine, undecidability poses a problem for automated verification. So we essentially want to move from being able to verify fully finite systems to being able to verify some parameterized systems automatically. And that's not an easy thing to do. But thankfully, a couple of years ago, along came a tool called Quicksilver. This is some existing work which has made some nice strides in tackling these problems. Quicksilver allows agreement protocols to be abstracted away using language-level primitives in a modeling language. And it also handles parameterized verification by implementing a cutoff reduction, which basically enables parameterized safety verification of certain types of protocols by model checking their instantiation with a finite number of processes. However, there's a big asterisk on these achievements, which is finite state processes. That's right. The individual processes in the system still have to be finite state in order for Quicksilver to be able to perform model checking. Now, this means that the processes have to have finite variable domains. And in fact, those variable domains have to be quite small if we want to fend off the state space explosion problem. So Quicksilver can verify a system with an unbounded number of processes by reducing it to a problem with a finite number of processes. But to verify doubly unbounded systems with unbounded processes and unbounded variables, we introduce Venus, which is an extension of Quicksilver, which utilizes a novel reduction to simplify this verification problem down to one that we can leverage Quicksilver's capabilities to handle. Now, to explain what Venus does, consider this process definition called consortium. It's written in Mercury, Quicksilver's DSL, and I'm going to use this as a running example. The protocol is roughly based on the arbitration mechanism for a consortium blockchain, in which a small subset of processes coordinate to make a decision for the entire system. I'm going to step through this definition and its behavior to try to help illustrate how Venus's reduction technique works. So the protocol begins with a series of declarations. These define some typed process variables and the communication events of the system, along with the associated payload domains of those events. This process definition has just one variable called data, and the rest of the process definition is really just control locations and event handlers. So if we imagine the system begins with all processes in the initial state, election. Here I've just shown 3 processes, but there could be any number. So we have these 3 identical processes, and each holds an initial default value of 1 in the data variable. Now from this location, they elect a subset of processes, the consortium, to decide on a value for all processes in the system. This particular handler says that up to 2 processes will be elected to go to a location to deliberate on what value to choose, while the rest of the processes go to another location to wait for the consortium to share that decided value. Now in the deliberate location, processes may be influenced by the environment to change their proposal value stored in that data variable. Let's say our 2 processes here get the values 9 and 7. Then, at some point, these processes engage in consensus, and they want to determine one value to agree on from the values they propose. Now, once that shared value is determined, these processes move to the decided location, and here they both hold the result of consensus, and they use a leader election protocol abstraction to choose one of the processes amongst the 2 of them to broadcast that result to the rest of the system, to the processes which are waiting in the wait location for that announcement. Here, the elected process is the red process, and the other process goes to the leader done location and stops. From the announced location, the elected process broadcasts the result of consensus to any processes in the wait location, such as this purple process here, and then it moves to leader done. And each process that receives the announcement then moves to the replica done location. Now the system is considered safe if any 2 processes in the leader done and replica done locations hold the same value in their data variables. Now, as it stands, Quicksilver can't verify this system because these variable domains and payload domains make the state space of each process unbounded. And Quicksilver requires finite state processes in order to check the conditions of its process cutoff reduction. So to reach a verification problem for which we can leverage Quicksilver, Venus has to first apply a reduction which targets the process variable domains so that we can simplify the verification problem to one involving still an arbitrary number of processes, but each of which have a small finite variable domain. At that point, we can pass it off to Quicksilver, and it'll take it from there to verify the system automatically. Now, if we take a closer look at our protocol, we can see that the data variable is only ever assigned directly from another variable or a symbolic value. We have some payload value domains of various messages, the result of consensus, and these 2 on the bottom right use this default construct, which is really just a symbolic representation of the initial value for that variable. There's no arithmetic or assignments by constants, and all that makes sense because this is really just a data coordination system. But more importantly, this system is exhibiting a property called value symmetry. This is a classical property, sometimes called data independence or scalar sets, but the basic concept is that values are distinct, but no value is treated as special. In short, the behavior of the system is invariant to permutation of the values that it's passing around. Now, another important thing to notice about the system is that when consensus takes place, the result of consensus, here denoted by this decision variable expression, is consistent among all the processes that participate in consensus. So when those processes carry that value to the decided location, there can only be a finite number of distinct values among all the processes that are there. The number of distinct values that they hold is determined by the cardinality of the consensus handler from which they get their value, which we can see here is just 1 in this case. And actually, by doing a little bit of extra analysis, we can see that all of these last 4 locations can only be accessed by processes holding a finite set of values, which is limited by the cardinality of consensus. And this forms the basis for what we've been calling a bounded region, which you can think of as just a set of locations where, one, we know that the processes there will have a finite number of distinct values among them, and which also includes all of the kind of important value comparisons across processes that we need to determine the correctness of the system. Now, outside of this region, we make no such guarantees about the number of values. There could be an arbitrary number of distinct values. But importantly, there are no comparisons across processes between the values that they hold when they're in locations outside of the bounded region. The behavior of the system doesn't depend at all on whether 2 processes which are not in the bounded region hold distinct values or the same values. That's important because that's what's going to help us kind of crush down an unbounded variable domain into something finite. And what we find actually is that when this system exhibits value symmetry, that allows us to kind of eliminate some of those unnecessary distinctness among those values while still retaining all of the relationships between data, the equalities that we need to expose any errors there might be in the system. Now conceptually, we can basically split the process state space into 2 sections. On the left, we have a region with no guarantees about the number of distinct values the processes can hold. And on the right, we have this bounded region where we can bound the number of distinct values held by any processes that are there at one time. In the unbounded region, equality between values in different processes makes no difference for the behavior of the system. So we could force processes in that region to share the same values when they might not otherwise, and verification won't be affected. This is what's going to allow us to collapse that unbounded variable domain. Now, on the other hand, inside the bounded region, distinctness of values across processes is critical to recognizing error states. So we can't collapse the values in that region to shrink the domain, but thankfully, the number of values in that region is already finite. So we can leave those alone and still get a finite variable domain in the end. So as processes move through the system, we get a trace of global states. If we look at this segment, say starting with a state where there are 2 processes, P1 and P2, in the deliberate location, P1 has the value 9 in its variable, P2 still has the initial default value. We also have a 3rd process in the wait location awaiting the decision from the other 2. And as before, we have an influence event. Process P2 gets a new value from the environment, say 7, stores it. Then P1 and P2 perform consensus. They agree on one of their values. They carry it to the decided location. After this, they're in the bounded region, so I've marked those locations in blue. And then one of them is elected to inform the other processes. In this case, it's P1 moves to announce, while P2 moves to the location later done. Finally, P1 sends the inform broadcast and the value 9. Everyone receives it and ends up in later done and replica done. So to reduce the domain of these variables, we consider each transition in this trace. And using a mechanism called a component-wise permutation, we can map the values in the original trace into a smaller range while still preserving equality within the bounded region and consistency of values that are transmitted with these communication events. But we, in addition to that, we allow values outside the bounded region to collide with other values which are outside of the bounded region. Basically, we can permute this 9 and this 7 both to the same value of 1 because outside the bounded region, it doesn't matter if they're equal or not. And that allows us to reduce the diversity of those values. And we find that for value symmetric systems with a bounded region like this, it's always possible to compute a component-wise permutation which limits the values of the system to a finite range. So by doing this for an entire trace, we have proven that if there's an error trace in the unreduced system, then there must also be an error trace in the finite domain system. So then, thus, by the contrapositive, if there's no reachable error state in the finite domain system, then there also cannot be any reachable error state in the original system. So then, to verify this system with unbounded variable domains, it suffices to verify this system with this finite variable domain. And in this case, we found that a domain of size 3 was sufficient to prove the safety of this system. So we performed a few case studies, which I don't think I have time to go into detail on. Basically, they fall into three categories. Consortium, we've discussed at length. This distributed register is based on the atomic register construct from the atomics framework, and key value store is a simple key value store based on Redis. So I hope I've convinced you that by some variable domain reduction with existing process cutoff reduction, Venus is able to efficiently verify some doubly unbounded distributed agreement-based systems. And going forward, we're actively working on using these techniques to enable automated verification for progressively more general classes of systems. Thanks for your time and attention. I'm happy to take questions.
Thanks for the talk. So just to understand your problem domain, I guess, all these distributed algorithms have been extensively studied in TLA plus and so on. And you can model check them, and furthermore, you can even apply TLA-PS to actually prove them correct for any domain or any size of the domain. So how does this relate to just using the TLA model checker, for example?
Sure. If I understand correctly, you're asking about proving these results in TLA plus for the protocols that are used inside the agreement protocols. Sure. So our approach is kind of modular in this sense. We're sort of standing on the shoulders of giants for those verified agreement protocols. You know, people did a lot of work to verify them on their own, and we said that's wonderful. We feel no need to repeat verifying those protocols. So instead, the semantics of the modeling language essentially implement an abstraction of those protocols, sort of an over-approximation of the specific behaviors that might be implemented there, so that from some state where we're beginning consensus, we end up in a state where the value is determined and consistent amongst those participating processes, and all of the internal details of that are basically left to the proof of the correctness of that protocol. So if we want to reason about a specific protocol, we just need for the behavior of that protocol to be one of many non-deterministic behaviors that we model in our modeling language semantics. Did that answer your question?
Maybe as a quick follow-up, so why not also instantiate the application in TLA plus on top of the protocol module?
So it's a good question. The goal of our approach is we're trying to kind of present, I guess, a unified template for expanding this decidability to like larger and larger sets of systems, which can be repurposed in a kind of a stackable way. So our hope is that as we develop more of these reductions, then you can kind of build up a lattice of systems that you can verify. And in order to verify a system which has many of these layers of complexity and unboundedness, hopefully at some point you really just need to come up with maybe one more clever reduction to kind of reduce your system into this sequence of verifiable systems and just have it take over from there. And TLA plus is wonderful, it's very powerful, but we're hoping that we can reduce the amount of work that would be necessary to bring a new system into that set of systems we can verify automatically.
Thank you.
Thanks.
Basically, I'm looking for a quick intuition from your side. There have been a couple of papers that have been saying that like this message passing is too low level for verification, it makes everything unnecessarily hard. And I'm wondering if this is something you noticed, and I'm also wondering like how deeply the message passing model is ingrained in your verification system. Sure,
thanks. It's a good question. For us at this point, the message passing it's a double-edged sword, because the more you want people to believe that your verification is, can be trusted and you've gone far enough down in the stack to uncover any interesting behaviors, the more precisely you have to model the message passing. For us, Right now, our communication model is a bit limited. We assume that it's synchronous, and the fault model is quite limited. But in kind of the spirit of what we're doing here, our hope is that in future we can add another layer on top of this, so that a parameter of the system might then be what are the exact communication semantics you're using, so that if you can step it down to something that's kind of nice and friendly, or even eliminate some transitions, you can basically simplify the verification effort and maybe even get some extra performance out of that verification.
Thank you.
Thanks.
Okay. Let's thank Christopher again.